Hi everyone, hope you are doing well. Welcome to my another YouTube video. In this series, we'll be working on our very first industry standard big data project. We will cover everything step by step, starting from creating Jira Cards, writing tactical and professional grade code, setting up infrastructure, deploying the code, scheduling workflows, and finally creating reports and dashboards. This is the overall pipeline we're gonna be implementing. And by the time you are done watching this video, you will be ready to add these things in your resume, showcasing exactly how you built an end-to-end big data pipeline. From capturing streaming data coming from Apache Kafka, setting up Google Cloud Storage as data lake, writing Spark Scala ETL pipelines for Dataproc, implementing SCD1 and SCD2 on Apache Iceberg, loading it all into BigQuery, automating deployments using Jenkins, scheduling workflow with Airflow, monitoring logs on GCP, and topping it off with actionable dashboards in Metabase. Let's get started. Let us understand the project requirement step by step. We have data related to YouTube trending videos coming from APIs and Kafka. Certainly, we will be simulating this scenario. We have a table which contains video ID and URL, and this table can only be accessed using APIs. You cannot use JDBC connector also. You can only do get or post request. Daily files are coming in our GCS bucket with just one column, that is video ID. You need to get URL associated with these video IDs from the table using APIs. We have data coming from two Kafka topics, VVLD and VT. Each contains different columns. VVLD topic contains video ID, views, likes, dislikes, and VT topic contains video ID and title. Load this data to Iceberg and then we will come back to next steps. We will start with the Jira Cards, the way we have in any actual project. This is the project we are working on, GCP migration. We can click on timeline and see the cards associated with the project. The first epic understanding project, we have these three stories. Let's see this one first. Download dataset. To download dataset, go to the link present in below description or search for Kaggle YouTube trending videos. Here, scroll down and download this US YouTube trending dataset in CSV format. You can sign in and you should be able to download. Now, let's explore this dataset. Set up a Spark Scala in your IntelliJ and read the CSV. So this is the dataset. We will be using video ID more like as a primary key and majorly columns like trending date, title, views, likes, dislikes, and thumbnail link column for our project. This is the Excel of Jira Cards which we will be following throughout the project. I've divided the project in around 42 steps. We are done with downloading dataset and exploding the dataset. Based on our architecture, we have to simulate fetching data through API. This is what we have to do. We have a database where video ID and URL is already present. We cannot just do select a star and fetch all the records. Rather, we can access these records only by using get or post method. So first step is creating a database with a table which has video ID and URL columns and then create APIs to fetch records. Run this Docker command and set up Postgres. This is the password and this is username. We can connect through DB World, link is in description. Edit connection, fill the details. And now create the table with video ID and URL column. Yeah, we have the table created. We have this tactical code load video ID URL db2 which populates our table, add a Spark configuration, invoke a Spark session. You can put your local path in here where US video file is present and give all these JDBC properties and run the code. The code ran and let's see the table. It should be populated. Yeah, we can see the data in our table. So the first step is completed. Now we need to create APIs to fetch these records using get methods. Let us mark this step as completed. We have this folder microservice, src, main. In resources, we have application.conf where we can have Postgres and driver details. Username is Postgres. We saw that before. And we can have these dependencies in our build.sbt file. Inside repository folder, we have these two functions, get URL by video IDs and get URL by video ID. It takes list of video IDs as a parameter. From database, it filters only those records where video ID is present. Get URL by video ID is similar, it's just that it takes just one video ID as parameter. Go to routes. We have API/v1/video IDs. We have post request and get request, which directs to get URL by video IDs function. This is the schema. It contains a schema of a table which is being used. You can use this test check code to see if you are able to connect to your table from your code or not. I've already tested it. This video API app is the main function which runs the server. We are using a Scala actor model here. It contains all the repositories and routes, and we have only one in our case, and then run the server on the given port. We can see server running on port 8080. We have simulated this step now, and URLs can now be fetched using video IDs. Now set up your Google Cloud account. You will get $300 free to use the services. We will be using this free tier only. Search for GCS and create one Google Cloud bucket for your project. Click create and give it a name. Create. I've already created it. This is my bucket, Y videos GCP POC. Inside landing folder, I have uploaded the CSV file we downloaded through Kaggle. Mark these two steps as done. Now create service account. Search for IAM. Click service account. Create service account. Give it a name. You can give roles here. You can add all these roles in your service account, starting with Dataproc editor. Logs view accessor, and you can add the rest. After you're done adding all of them, click done and your service account will be ready. Click on your service account. Go to keys. Create a new key and you have your key downloaded. Now go to your environment variable and add this. Google application credentials followed by path where the JSON is present. It will be in your downloads folder most likely. Mark this as done. Now we need to generate daily files which has video IDs to fetch their corresponding URL through APIs. This is just like any usual scenario where daily data comes in any storage and we need to hit some other database to get more details for those daily data. Here we have video IDs coming and we have to hit the database to get the URL. Let us see how we can achieve that. Ensure you have service account credentials stored in environment variable. We have our main Kaggle data present in GCS bucket, which we will be using to populate source systems. Select video IDs from that CSV. Then randomly select 1000 records, separate it with the spaces, get current date time, and load records in that daily file folder. Let's run the code. Go to this path and see how daily files look like. Go to cloud storage, buckets, source, daily video, and then timestamp. And yeah, here we have the file. These kind of files you will be getting in your source system. Here we are just simulating that scenario. Download the file. And we can see video ID is separated by space. Now coming to next step, to fetch URLs for these video IDs using APIs. Inside microservice folder, we can see server will be hosted on port 8081. And in route section, we can go to API, V1, videos, URLs, and pass the list of video IDs to get URL. This particular section filters from database only those video IDs which we are passing as parameters, and then it runs the query. Here we have defined data type of all the columns present in the table. Now before writing code for it, let us do this using Postman. Download Postman and install it. Click on send new requests. We have defined a post method followed by the URL we have set in route section. In body section, we can pass list of video IDs. Make sure your database is working perfectly fine and run your app on port 8081. We can see server started. Change it to 8081. Give this path and pass list of video IDs and run it. We can see we have got corresponding URLs for all the video IDs we passed. Let us mark these things as done. Now let's write the code for this, as we won't be using Postman for the video IDs coming on daily basis. This fetch API contains all the code. Import HTTP client and play API library. Start a Spark session. Give a schema which will just be video ID. Now read the data. I have hard coded it, you can parameterize it. Split the file with a space and create data frame. Now using implicit, we will convert both request parameter and response parameter in JSON format. We have this function fetch URL for batch and pass video IDs. Then we have this request URL. Then post request with this request body and request URL and save the response. Now parse the response and collect it. This is the output, a schema with video ID and URL. And the video IDs which we are getting from daily file, we are grouping in hundreds so that server doesn't crash handling so many records. And call that fetch URL for batch. Convert the output in required format data frame. Run this app. These are the video IDs grouped in 100, and this is the corresponding result based on that. Check the server logs. You can see we are requesting these 100 video IDs every cycle and getting their corresponding URLs. Let's mark this step as done. Remember, we are not following standard coding patterns now. We'll do that later. Next step is simulating Kafka setup to receive data from Kafka topics. We have covered fetching data through APIs and will be loading data to our warehouse, Iceberg, in some time. But here we have one more scenario to fetch data from Kafka topics. To do this, we will be sending data to the topic. We have two topics in here, VVID and VT. Let us see data we had from Kaggle with all columns we're gonna use to populate these topics. VVID will have video ID, views, likes, dislikes, along with trending date. VT will have video ID and title, again along with trending date. We are assuming that we have two different topics in which these data are coming from source side. We have to consume and process it and put it in Iceberg in required format. First, let's start with setting up Kafka topic. Get this Docker Compose file. We have Kafka with three brokers, Kafka 1, Kafka 2, Kafka 3. We have Kafka UI. Also, we have a schema registry, which we won't be using in this video. And we have this network, my network. So first create that. Docker network, create my network. I've already created it. Now open this in terminal and do Docker Compose. We can see all our containers started running. Let's go to Kafka UI. And we can see three brokers here. We do not have any topic created as of now. Add a topic VVID, 3 replicas, 7 days, and create topic. Again, add another topic, VT, partitions as 3, 7 days, and create it. We have these two topics in our Kafka. Now write the code to populate these topics. Go to VVID populate code. Write all the bootstrap server address, topic name VVID. Create case class specifying the schema of VVID. We take data from GCS where we have stored our Kaggle data. Load data of a particular trending date from our dataset. Format your trending date, which is in different format. Now consider this video ID as key and entire records as value. Write it in Kafka. Run the code. Open Kafka UI. We can see VVID has 200 messages. We can see each video ID is key with the entire record as value. Do the same thing for VT topic. Run the code. Check VT. Yeah, we have 200 messages for VT also. Open it. See the messages, we can see title and load date. Mark these steps as done. Yeah, we have loaded data to both these topics. Now, till this part, you will be having data from source side already available in any actual project. This was just a simulation. Let's talk about consuming data from topic. We have data present in Kafka, and we have to write a Spark Scala code which takes data from here and loads to Iceberg using SCD1, SCD2 on Jupyter Notebook. Let's start writing the consumer code. Enable these configurations, give bootstrap server names, have a checkpoint path and load path where we are loading these build records. Read the data from topic and load it on the basis of load date. We can see VT folder in our bucket with load date and data in Parquet format. Do the same thing for VVLD. Load the data in GCS. Mark this step as done. Now next step is to take the data and write it in Iceberg applying SCD1 and SCD2. Before this, let us understand what are we trying to achieve.
We have got data coming in our GCS bucket for VVLD and VT. VVLD data is coming in this format. For each of the load date, we have got video ID, views, likes and dislikes. Now what I want is, in my Iceberg table, whatever is the present state of data for that particular video ID, that should be reflected as is. For example, for this video ID 101, this is my views, likes and dislikes. This is what I want to be reflected in my Iceberg table. Now, next date, for the same video ID, we see views, likes and dislikes got increased. I want my Iceberg table also to be updated with latest date for that particular video ID with latest views, likes and dislikes. This is basic SCD1. Now for VT, I want SCD2 to be implemented. Let's say our load date is 15 December and for video ID 101, we have got title as ABC. Now I want same thing to be present in Iceberg table with this flag as true. And on next date, if let's say for load date 16 December, video ID 101, title got changed from ABC to ABCD. Now what I want is, I want previous data to be kept as is with flag as false and new data should be inserted with the updated title and flag as true.
Now let's set up Metastore and Dataproc cluster. Come to Google Cloud and search for Dataproc. Go to Metastore, create Dataproc Metastore 2. I will set the size to minimum as we don't require much and this is very costly service. Rest we will leave as default and submit it. It takes around 25 to 30 minutes to create it, so wait till then. Now it's active. Go to clusters, click create cluster, cluster on compute engine. Select the default subnetwork, select Metastore service which you created just now. Here we will select Jupyter Notebook. Machine type as enter standard 2. Select the standard persistent disk. Change disk size to 200. Same goes for worker nodes. Standard persistent disk 200. Select cloud storage bucket. Pick Y video GCP POC, the one where we are storing all our files, and create it. Wait for some time and our cluster will be running in some time. Go to cluster, web interfaces, Jupyter Lab. Meanwhile, go to VM instances and SSH to the master node. Go inside var lib spark, go to jars. We need to put few jars required for Iceberg. I already have kept these jars in my GCS bucket. You need to download it first. Search this jar name and you will find it in Maven repository. Click on this version. Click jar. You can download the jar and then upload it to GCS bucket. Similarly, do it for the other one. Now we need to copy these two jars from bucket to this location. Do it for both the jars. Now search for Dataproc. We need to restart the cluster, so stop it and then start it. Let us populate our Kafka along with consumer with few more records of other dates. So we have data of 14th, 15th and 16th date for VVLD. Do the same for VT. Yeah, we are done. Refresh it. You can create a new notebook and this jar and you can add this jar in config section along with other Iceberg configurations. Go to Metastore, select this script URL and paste it here. This warehouse is same as project name. Write a Spark SQL to create table. The consumer code which put data in GCS bucket will be using it. Using this snippet of code, we're gonna load the data and write it to Iceberg table, which we just created in Y video VBLD data. This is my intermediate table. Now we can do select a star and see the records in Iceberg. Since we loaded the data of multiple dates, so we can see this particular video ID was present on two dates, 14th and 15th. And we want our final table to be updated with this latest record only, that is the one in 15th. Since we have just two executors and if both are occupied, we need to kill one from here. Write this command and then it will delete it. Let's run it again. We can see we have both data table and target table created. Now from the delta table, we pick the ones with the latest record and create a temporary view from this. This is my merge query. We join both source and target on video ID, and if they match and source load date is greater than target load date, then all the corresponding columns of target table is to be updated. And if it doesn't match, then the records have to be inserted. And this is basic SCD1. In first run, we won't see anything as our target table is empty. But from second run onwards, target table has to be updated for the records present in source table. Now load for 15th. And here we see these records are updated and their new values have come in data table. Let's pick this video ID and see. Yeah, we get multiple records. And for same ID, if we check in target table, we can see just one old record. Now let's run the merge query again. This is gonna update our target table. Now if we check our target table, we can see this is updated. And now coming to another scenario where we have to apply SCD2 for VT table. Again, do the same thing. Add Spark configurations. Create VT delta. Now load data of 14th in Iceberg VT delta table. Create VT target table. Again, create a data frame and select those with latest video IDs. Write merge query. If video ID in source matches video ID in target, but there is any difference in any other column, like here title column, then update the flag parameter to false and end date to that of source date. Now again write the merge query, and except for the records where video IDs match and current flag is true, we insert remaining video IDs. And you can pause this part of the video and just see what exactly I did. So, or you can even Google what SCD2 is actually. Since it was the first time, load and target table was empty. We won't see anything, but let's load again for 15th. And we find few video IDs where title is updated. Let's pick this video ID and run it. We can see this column is added on 15th. Run this snippet again. And run first part of merge query. We will run it in parts this time just to show how data changes after every step. Copy this and paste it here. We can see it has added end date and changed the flag is current to false. Now let's run the second half. This is gonna insert the record which has updated title. See the target table? We can see it has added a new row along with maintaining history. So yeah, we have covered a significant portion of our data pipeline, and let's mark it as done. Now enable BigQuery. And create table for DBLD. Similarly, create table for VT. So we have these two tables created. Now run this script to load data to BigQuery. Update Metastore URL. Write dataset as the one you created in your BigQuery. Read data from Iceberg. And format load date to date format. And give a temporary bucket here. We'll put mode as override. I can do the same for VT table. Now go to BigQuery table. Open query and see the data. Here we can see the data is loaded. Yeah, so we are done with loading data to BigQuery. These are the files we used for our project, but they are for tactical purpose. This is not how we're gonna keep in actual project. So let's standardize our code. First, go to resources. And you can add these GCS and Kafka paths and location for dev and prod environment. We will refer these parameters from here. Now inside the Scala, we can have company name, and let's say we have multiple projects, so we can even have project name here afterwards, but here I'm just going with the Scala com and company name. And then create folders here, API, batch, DDLs, framework, some interim, output, schema, setups, and stream. The most important folder is framework here. It contains config, controllers, jobs, utilities, and our main app method. Let's see the config. We have app config in here. Based on the environment in which we are running our code, it takes the path mentioned in that resource conf folders. We set environment in environment variable, then load the respective configurations. We have Spark config. We mentioned here the Spark session configurations, the default ones which we can edit it later for different codes. And we have a trait, a Spark session provider. We have job section. Here we have a trait job which contains generic extract, transform, and load methods and a run ETL method. We have enums which contain each of the jobs. All batch and streaming jobs have to be kept here in this format. And we have a job factory. Here we take each of the job, create its object, pass its relevant controller as argument, and here we have each of the controller mentioned. And the configuration of each of the controller is present in controller folder. We can separate each of the controller with respect to folders in which the main working code is like API, batch, and stream. Now let's see inside batch. We'll have a job video processing. We create a Spark session. Here we can put app name, required driver memory, executor memory, codes, executors, and take other generic Spark configuration from the one we saw before, and we can even overwrite it. Similarly, for fetch URL controller, we can have its own configuration, and the same goes for all stream jobs. Now we have this one common main app for all the code. We just have to change job name and controller name by passing them in arguments. Then we create job and use its respective controller and then run ETL. This run ETL invokes the corresponding extract, transform and load function. Now see the actual code where we have overwritten our extract, transform and load methods. We pass controller here and it extends the job trait to have those methods. Then we override those methods. Path and all we are taking from config based on the environment. And we have some generic utility methods created, such as read CSV, write parquet. You can keep enriching it based on your general purpose transformations required in your project. Now coming back, this is GCS landing bucket. Path is dependent on environment again. And here I have changed few of the parameters from the generic one. And the output of extract is given as argument in transform. The output, as we can see, is a map, and we can even have multiple data frames returned as output of extract, which can be used in transform method. And output of this transform method can be used in load method. Similarly, we have fetch data through APIs. This is code for that. This is kind of same as we have seen earlier, and we do not have much of transformations here. Now, as we have seen, we have main app where we have to pass arguments. This is how we can do it in IntelliJ. Take the job name, it's a video processing job. Click edit and pass arguments. Job and controller here, like this, separated by spaces. Click OK and then run the main app. You can see our job is running. And yeah, the job is now successfully completed. So this folder structure you can follow for any of your big data project. If you even want to include secret manager and other things, you can refer code provided in this repository. Let's mark these steps as done. Now coming to setting up Jenkins, I have a separate video of setting up Jenkins. You can check in the description. Where you can follow things like installing Java, SBT, Jenkins, Git, and everything. After doing the setup, SSH into that instance. Write your IP and port 8080. Open your Jenkins. Log in with your credentials. In this video, we will mainly be focusing on setting up our CI/CD pipeline. And this is my CI pipeline. Give your GitHub project ID and write this pipeline script. Give branch name as parameters. Go to Manage Jenkins. Click Credentials. Global. Add credentials. Select secret file. Choose the JSON file you created long back from Google Service account with the required access. Add GCS bucket. Another stage is checkout. Checkout from the branch name, then build and assemble jar. Go to your root folder and do SBT clean assembly. Now authenticate it and upload the jar to GCS bucket. Save this, build with parameters, give branch name as main and build it. You can check the logs, Jira is getting created. Now see where we are uploading this jar. Okay, jar will be added in this artifact folder. Go to GCS, buckets, artifact. Here we can see branch name main, and inside this we will have a jar. Yeah, here we have. So this was our CI pipeline. Coming to CD pipeline, click configure. Have these two string parameters, job name and controller name. Write this a script to submit your job to Dataproc cluster. And this is my Dataproc cluster ID. Class, bucket, branch, job and controller we have parameterized. Now after we submit, we do not want our Jenkins job to keep running till our Dataproc job is running. So we will just take job ID and will monitor the job from outside. That's why we need to put this async and quiet mode. Again, build with parameters, pass branch name, class name, job and controller name, build it. We can see in console we got job ID. Now go to Google Cloud, jobs, click on the job ID, and here we have our logs. We can monitor it from here. We have just kept limited executors, so if it doesn't get enough resource, we can go to master node of Dataproc cluster and kill applications which we are not using. After doing this, we can see our job has started giving the output. To stop it, we just need to click a stop. So now we have covered setting up Jenkins, CI job, CD job, and we have even monitored the logs. Coming to next step, we have to visualize it on Metabase. We have our data from Iceberg to BigQuery. Let us see how we can visualize this data. To do this, we can run this tool Metabase on Docker and do docker pull Metabase. And then do docker run on port 3000. Wait for some time and run on localhost 3000. We can see Metabase is up and running. Fill this form. Give any company name. Create password. Then select BigQuery. Give some display name like UI videos analysis report. Go to Google Cloud and copy the project ID. Now select service account JSON file. Finish and take me to Metabase. We see it is unable to fetch any BigQuery tables we created. Okay, you can go to your service account, edit it, and add BigQuery data viewer and BigQuery job user role. Then we can see all the tables. Now click on it, and you can see some reports are automatically generated. You will have better insights if you have multiple columns present in your table. We have got just very few. You can see many more reports on the basis of different columns, and Metabase is intelligent to create a few for you. Now, coming to scheduling job, we can do it using Airflow. This is my Airflow section. Here we have .env folder which contains Airflow UID and a Docker Compose file to set up Airflow anywhere. Open it in terminal and do Docker Composer. We can see our containers are created. We need to do some pip install to have these libraries and create a DAG. We have just one DAG. Now in a Spark job, give the required parameters which we give in Jenkins to run the job. Provide main class. Give GCP path where your jar file is present and the arguments. We will use Dataproc submit job operator to submit our Spark job. Log into your Airflow. You can search for your job here. We have submit a Spark job to Dataproc. Click on job and trigger that. Yeah, it is failing because I have turned off that Iceberg Metastore we created, as that is very costly service. But we can see it is running. Go to XCOM. Here we have job ID and project ID. Copy this job ID. Go to jobs, and yeah, this is the one. We can see the logs, it was running fine, and just that we turned off Metastore service, it is unable to write data on Iceberg, so it failed, but yeah, rest is fine. Now we are done with this last step. And we can add tons of things in our resume, and we should be able to defend it in interview as we have now, in good hands-on experience on this. Give a detailed overview and that how we created a scalable and robust pipeline to analyze data of a social media company, and talk about key responsibilities involving Kafka, Google Cloud Storage, and how you applied SCD1, SCD2 to Iceberg tables, how we use Google BigQuery as warehouse and then used Airflow for orchestration, how we use Jenkins to set up our CI/CD pipeline, and we monitored logs using Google Console and created reports on Metabase. We can even talk few of the key achievements like these. Yeah, so that's all for the video. Thank you, and do subscribe for more such videos.